There it is. So then the floor is yours.
I think I don't need the mic. Yes. Hi, hello everyone. Yeah, so many familiar faces, but my name is Zizhen. I'm the cohort 2 fellow in the robotics and automation schemes, and now I'm a lecturer in the computer science in Loughborough University in UK. So today I'm presenting work in collaboration with Zizhen from Resilience and Williams in the National Highway. And this is my last piece when I'm still in the feature road. And yeah, so the story is basically focused on the winter road maintenance. First of all, what is winter road maintenance? It basically, in one single sentence to explain, is you send a trunk with fully occupied salt, and when the vehicle's driving, you spare the salt. And the salt will be landing on the like iced road or snow road, melted, and to protect to protect the road surface safety for driving. So that's the winter road maintenance. And surprisingly, we're all thinking should be a very easy job, right? You just send the vehicle and going through the route. But in reality, it's very difficult because there's no such autonomous vehicles can drive and spare the salt. They need a driver. But driver, they only have their own experience about driving in the national management road. So, and also there was another constraints is the well-being and health of the drivers. So they have limited working hours. So in practice, each drivers can only drive as long as 2 hours per shift. Then they need to take a break. So combine all those things, it become a very extremely difficult optimization problems. So this is why we coming with this project. So yeah, this if you can see from this map, this is actually given by the National Highway, and this will be our proof of concept story. And yes, so this 3 house labeling is our depot, because all the vehicles overnight, they couldn't just park in any place. They need to stay in a storage, doing some repair, or even uploading more sorties. So they have those 3 depots to collecting or storage all the vehicles. And those red routes is because we are talking about national highway. So those roads are labeled as M road, managed by the nationwide, not local authorities road. And the national highway only representing or responsible for those roads. And we need to and those red labeled road are the road need to be treatment. And then this is the algorithms we are trying to propose to solve it. It's a bi-level framework. Bi-level means 2 levels. So we have this upper level block, which is we're using a policy-based agent. Basically, it's a reinforcement learning agent. And more practically, we're using PPO to handle the strategy micro-level decisions. It looks over the whole map and dynamically assign each specific road segment to specific depots. And those depots will send the vehicles to treat those segments. And then the low level is more like a constraint-aware routing algorithms, another agent. It's working as an operation design agent, and it takes the assigned territories from the upper levels to then run optimization algorithms or the routing planning algorithms to find the best route for the vehicle sending from the depot and to treat those assigned road. So that's basically the whole story. And then by combining these 2 bi-level frameworks, it creates a feedback loop. So the upper level agent continuously refines the strategy map based on the actual covered emissions and the driver's working load, report back to the low level routers. And then the low level routers make the optimizations for the path planning, then feedback. So this is interactive between them. Good. So here is because we are talking about Department of Transportation's carbon emission is very important. So in our problems, we are not solving single objective problems. We are solving multi-objective problems. First one is minimize the emissions. Second one is for the safety and the healthy and the well-being of drivers. We're trying to minimize their max speed, which is their driving times. So this is a multi-objective optimization problems, and obviously there's a trade-off between these two objectives. So here is the result. Here, like, we track the system's performance across the multiple iterations over a 60 by 60 kilometer section of the UK networks. So you can see the map scheme, the blue one, well, the maximum times any vehicles is out of the road, and the total fleet emissions, because in total each depot can maintain at least 2, otherwise it won't call it fleet. And we have 3. We have 3 depots. So it's a quite remarkable, because the most significant, well, improvement happened in very earlier, like in the first 4 iterations. Right? It find the best, or find the so-called pseudo-optimal balance where the working loads are evenly distributed, and it can avoid in the situations where like one depot is overwhelming and another one is just silence. So it's proof, the figures prove the algorithms is work in a small areas. Even the small areas is 60 times 60 kilometers, just keep this in mind. And then, so previous pages is basic number, and this one is more reality. We're testing different algorithms. So we have our baseline algorithms in the left and our optimized algorithms in the right. The baseline algorithms, we're using a very simple assigned algorithms in the upper level, is the KDT tree, and we're using neural networks in the low levels. So it shows some result. It shows a valid result, but you can see how massive the route they're planning. And here, right-hand side, we have our optimized combinatorial. We were using the PPO and one heuristic optimization algorithms to the path planning. And this map is the algorithms we obtain after 10 iterations. You can see how clear it is. And yeah, this pages is the last result we're reporting. As I mentioned, this is multi-objective problems. We're trying to aim in both the map scheme, the driver times, and the emissions. So you can see, comparing by just see the numbers, you will see there is maybe not very huge, but it do has reducing for the driving times and emissions. But most significantly, because per the requirement from, I think maybe the staff unions, per driver couldn't work in more than 2 hours. So we're reducing it from more than 2 hours to less than 2 hours. That's totally match what's the National Highway or Department of Transportation requirement. And also you can see 4% to 5% reductions in the carbon emissions. So this is the final result. So to conclude, this is more like a small research. It's more like a proof of concept, but we want to look at where we can take in this technology next. So our vision is to expand these multi-agent ecosystems to like facilities seamless cross-boundary cooperation between national authorities to local authorities, because this winter road maintenance, as we said, the road, even we drive in the road, for treat them equally. Some are maintained by the national and some are maintained by the local. And surprisingly, for this winter road task, National Highway only care about the national road. And even they will drive through local road to attend those national road for the assessment. They won't spare thoughts doing those local road. And the local road, same things. So they are, well, wasting a lot of driving times, wasting a lot of like carbon emissions for the drivings, but do nothing. So we are thinking if these technologies can be used to like put the national wise to the local wise together and trying to deal with each other, negotiating with each other, there will be more efficiency and financial, environment friendly. So I think that's the most things I want to introduce. Thank you very much. And thank you for the Future Road Funding.